All right, section 8.3, we're going to look at a confidence interval for a population mean. Okay, so this would be our formula for a one sample Z interval for a population mean. In 8.2, we did Z interval for population proportion. Now we're going to look at the mean. All right, there's a couple of problems with this formula. If we don't know the population mean, we probably don't know the population standard deviation either, because we would have to know the mean to calculate it. All right, so what could we do? Well, we could use SX, which is the sample standard deviation. But when we do that, this was a confidence interval or a bunch of confidence intervals that were created using the sample standard deviation. All right, and we used a 99% confidence level, but only 92.5% of our intervals actually captured the true mean. So that won't work either. We need a bigger critical value. That Z-star number does not work. It doesn't get big enough with the sample standard deviation. All right, so we use what's called a T-star critical value that comes from T distributions. So T distributions look similar to the normal distribution, but they have more area in the tails. They are up here farther away. They account for more variability. There's also an infinite number of T distributions because it's based on something called degrees of freedom, which has to do with the number in our sample size. Okay, so this is the formula that we're actually going to use. X bar, the sample mean, plus or minus our T-star critical value times the sample standard deviation divided by the square root of our sample size. When we do the T-star value, okay, the degrees of freedom is always n minus 1. Okay, so degrees of freedom is our sample size minus 1. And then for the area in the calculator, we're going to do just like we did with the Z-star values in 8.2. 1 minus our confidence level divided by 2. Okay, so to get that T-star value, we're going to use our calculator. All right, so I have a TI here. It's going to be very similar to the way we did the Z-star. So I need the distribution menu, so it's going to be second distribution. We did inverse norm when we were doing the Z critical value. For a T critical value, we're going to do inverse T. All right, so I'm going to go there to inverse T. And then just like before, we got to put in our area. So if I am doing a 95% confidence interval, that means that I have 5% on each tail, and I divide that in half, so it's going to be 0.025 is going to be my area. The degrees of freedom is 1 minus the sample size. So this was a sample size of 12, so my degrees of freedom are going to be 11. And I go ahead and press enter, and eventually there's my T-star value. Just like the Z-star in the last lesson, we're going to take the absolute value of this. Okay, so my T critical value would be 2.201. All right, now on a Casio, we're in the stat menu. Okay, distribution. We want a T distribution. Now, my little computer calculator does not have inverse T right here. Yours should. Right? I don't have one in front of me to check, but I'm 99% sure that whatever Casio you have has inverse T right here. It's just my little computer one that doesn't. If not, please let me know, and we can either get you a different calculator, or I can show you how to do it old school and use the T table. All right, so we got that 2.201 value, and then the second one, we want a 90% confidence interval, so this time my area is going to be 0.05. I have 10% left over. 10% divided by 2 would be 5. And then my degrees of freedom is 1 less than my sample size, so 47. Just like with our confidence intervals for proportions, we have conditions that have to be met. Okay, so our sample has to be random. We still have the 10% condition, which means that our sample has to be less than 10% of the entire population. And then this time, instead of large counts, we have the normal or large sample condition. All right. So here they are written out. Now, that normal large sample, there's 3 ways that that condition can be met, and we only have to have one of the 3, okay? The first one is if we know that the population is normally distributed, okay? Then it doesn't matter what size our sample is, it doesn't matter what our sample looks like. If the population is normally distributed, we can use this t-interval. If our sample size is large, meaning that n is at least 30, we can use a t-interval. If we don't know either of these things, okay, we don't know the shape of the population and our sample size is small, what we're going to do is we're going to look at a graph of our sample data, okay, and as long as the graph does not show strong skewness or outliers, we can assume that it's close enough to normal that we can use the t-interval. All right, so let's look at what that looks like with some examples. We have 50 students, and then we have a histogram of their GPA. Is the normal or large sample condition met? In this case, the graph is irrelevant. Our sample size is 50. 50 is bigger than 30. We're good to go. Okay, now we have this where we have 20 randomly selected pieces. So we have a sample size of 20. We don't know anything about the population distribution. So I'm just looking at this stem plot. And if I were to kind of draw this distribution, we can see that this is pretty clearly skewed. Most of my data is right here. And then I have these ones, these 230, 240 could maybe even be considered outliers. So we would say no, the normal or large sample condition is not met because our sample size is smaller than 30 and our sample data is strongly skewed to the left. Okay. Here we have a sample of 20 students. All right, if we look at this box plot, all right, now this right side is longer than the left side, all right, but not extremely so. And there are no outliers because outliers in a box plot would be marked with like little stars or asterisks. So we can say here that yes, okay, even though our sample size is small, the box plot is not significantly skewed. Okay, so when you're looking at these things, if you look at it and you're like, I don't know, it's probably good. You can probably say the condition is met. If you look at it and you go, nope, that is clearly skewed, then we would say no, the condition is not met. So it has to be obvious. All right, and something that's important to know in any free response situation, okay, if your sample size is smaller than 30, you have to sketch a graph. Okay, if it's not provided to you in the problem, you need to make a little sketch. You can draw whatever graph you want. My suggestion is a dot plot because it doesn't require you to do any math. It's the easiest one. You know, a histogram, a box and whisker might be super easy to do on your calculator, but you have to draw it anyway, so you might as well just do a dot plot. All right, so once we have determined that we can use the t-interval, then we're back in our SPDC, okay? So the same thing we did last year. So here's our example problem that we're gonna look at. I'm gonna let you pause and read that. And now let's go through our steps. So first step is state. We need the confidence level and we need to define our parameter. So in this case, mu is the true mean number of books. All right, for our plan, that's where we're gonna check our conditions. We're gonna say we're gonna use a one sample t-interval. All right, and let's check our conditions for that interval. Is our sample random? Yes, they told us it was random. Do we meet the 10% condition? Yes, it's reasonable to assume that 1,520 is less than 10% of all American adults. And then last one, do we meet the normal / large sample condition? Our sample is bigger than 30, so we're good there. All right, so now let's go ahead and do it. We were given the mean and standard deviation. We can use a calculator to find that t-star value. So let's go ahead and do that. So I'm going to go to the distribution menu. I want number 4 inverse t. My area is going to be 0.025 because I'm doing a 95% confidence level. My degrees of freedom are going to be 1519 because that is one less than my sample size. All right, do that math, and I get a negative number, but I'm always going to use the positive value, so 1.962 would be my T critical value. All right, and then we're plugging that in our formula. So sample mean plus or minus T star value times standard deviation divided by the square root of the sample size. All right, simplify this, add and subtract, and here's our interval, 11.09 to 12.91. And then conclude, we're going to interpret, and it's that same interpretation sentence. So we're 95% confident that the interval from, plug in your numbers, captures the true mean number of books read by American adults. All right, second part of that question is, Pew said that adults read an average of 14 books in the previous 12 months. Does our interval provide convincing evidence that the mean is different than 14? We would say yes, because 14 is not in our interval. All right, so anything not in our interval is not really plausible. So I'm going to say we have evidence that 14 is not really the true number. All right, free response tip. If you're asked to construct and interpret a confidence interval, this is a good bet that the conditions are met. However, if you want full credit on that problem, you still have to state the conditions and show that they are met. Okay, so even though we can assume that they are, we can't assume in terms of the FRQ because you have to write it out. Okay, important note here, in a multiple choice situation, you may be given a scenario where the conditions are not met, and there would be an answer choice where you could indicate that the conditions are not met. So bottom line is, always check conditions no matter what. I want to look at one more example where you're not given summary statistics. So here we're just given a list of data. You can pause and read through this problem. But they don't give us the mean and standard deviation. They just give us the data. All right, so still same thing, state plan do conclude, okay? Still checking all of our conditions, and this would be a case where, because our sample size is less than 30, we would need to draw that graph. So like I said, I would draw a dot plot, okay? It's simple and easy to make in a time test situation. And so if I look at this dot plot, there's not really strong skewness, nothing's crazy, so yep, condition met. All right, now for the do part, I just want to remind you about finding this information in your calculator. So this would be where we would put the numbers in stat. All right, so you can see I've already entered them here in your Casio. Same thing, menu stat, and we're entering those numbers there. Okay, and then just a reminder of how to get that information. We did this earlier in the year, but I'm going to go on a TI, I'm going to go back to stat, go over to calc, and I want 1var stats. Make sure this frequency list column is empty in this case. All right, so if there's something there, take it out. And then we calculate. And then on your Casio, it would be calc 1var. All right. Again, make sure that over here in your settings that frequency list for 1var frequency, that just says 1 and not a list number. Okay. Now with these numbers, biggest thing that I want to point out is when you get the standard deviation, make sure that you are using the sample standard deviation. Okay, so that SX number. I know mine look crazy over here on your screen. It won't show up like this. It will show up as sigma and SX. So because we are dealing with a sample data here, we have to make sure we're using the sample standard deviation. So we're using that 36.209 number and not the population standard deviation. Okay, very, very important. All right, but same process there, and then our same conclusion. Okay, and then last thing is same as we did in 8.2. Sometimes we have to be able to find a standard or a sample size for a desired margin of error. Okay, in this case, we are going to use that original formula from the very beginning, the Z-star formula, and we're going to use an estimate from like a pilot study for our population standard deviation. Okay, and then just like we did before, we're solving this equation for n. All right, so we have an example here. I'll let you read through that. Okay, and so we want a margin of error of 1. The z-star value here would be 1.96. You can get that from your calculator, all right? That's going to be in your distribution. It's going to be inverse normal, right? And then 5 is the estimate for standard deviation. And we solve this thing for n, we get 96.04. We're always, always, always going to round up. So we would need at least 97 monkeys to estimate the cholesterol levels based on the parameters that we were given. An important note, this is the only place, all right, when we're finding a sample size, that's the only place where we're going to use that assumed or estimated sigma, population standard deviation. Do not do that when we're doing a confidence interval. All right, when we're doing a confidence interval, use the sample standard deviation and the t critical value. All right, and that's all we got.